Here's our topic. Here's our objective. And if you look in chemistry, there's like several Ks. All right, which K is it? It's the K about rate law. And I want you to state some facts and be like, hey, here's how you calculate it. Now, if you look at the reference sheet, you're going to see a K here, there, all those, one down here, and on the back, there's two more. There's one here, and there's something right there. Now, this K, the first one is kilojoules. Kilo means 1,000. This one is the equilibrium constant. The one on this one over here is Kelvin, and the temperature Kelvin when you're dealing with gases. And the one on the back, with the last one, not by any means the least, is the one that deals with the Gibbs free energy. Now it's none of these four. It's the one here on the bottom. We're talking about the rate constant K. Now you remember that I said Q. Q has to do with equilibrium. It's often like symbol in some ways calculated as K for equilibrium, but it's not that. So it's just the one about the rate constant. Here's its definition. This comes directly from the Tro textbook. All right. And K has to do with experiments. All right. It's a rate constant that tells you how it influences the rate. And the first thing to think about the K is it's a number. All right. And what do the numbers mean? We're going to neglect the units now. In general, the bigger the number, the faster the reaction. All right. Because if you get a really big number, you have any concentration of reactants enough to react, it's going to go fast. All right. Now, the next thing to think about or to know about K is you look at this graph here. This comes from ChemLibra, right? I'm not sure if you're going to be able to click on that. This is the hyperlink. You'll notice two temperatures. That's because K is temperature dependent. If I change the temperature, I'm going to change the reaction or change the value of K. Now, I just want to go back to the reference sheet, and I want to make sure you understand that this rate constant is not these three. It's this one, and this is what it means. The other threes mean these three things, all right? But we're talking about the rate constant one. Now, why is Dr. Square going to the lab? Well, these values have to come from the lab. They have to be experimentally determined by studying the reactions. I want to bring back these two reactions. This also comes from that ChemLibra site. You'll notice the values are different. These K values are reaction specific, and they're going to be independent of reactions, or every reaction is going to have its whole slew of values. Now I want to bring out the units, and you'll notice that these units are different. It's got 2 molarities, and this one's got 1 molarity, and this one's got 2. The reason for that is the rate constants units depend upon the order of the reaction and of the rate law. So here are some overall orders. If the rate is just K, if that's general rate law, the units of it are going to be molarity over per inverse second. And here we go. First rate, it's just inverse seconds, and here's second, and here's third. And one thing to consider with this is all of this makes a rate. So you need a concentration change per unit time. Now, how would I solve for K? You're right, I'd have to go to the lab. So we're going to do an example. This comes right out of right out of Tro. And the solving for K, the formula is your rate from experimental data divided by your concentrations. It's going to depend upon your rate law. So for this one, it's just the rate divided by the concentration of nitrous dioxide squared. So here's some data. I'm going to choose trial 2. I'm going to plug in. It wouldn't matter which trial you use, all right? Now I'm going to square it, and then I'm going to solve it. And that's my answer. So that's my K value. That's go right there for this particular reaction. Let me know if you have any questions or comments. And thanks for listening. I'll take it easy. Bye. Here are my sources.